In this lecture, we are going to see basics of queuing models. Queuing models are also called waiting line models. Here we study what happens when an individual or a set of people come and join queues. We are quite familiar with queues in our day to day life. Common examples of queuing models that are discussed that we encounter are going to a doctor or going to a barber shop. A queuing system essentially happens when there are people or entities who arrive, who are called arrivals, who require a kind of service from another entity. So, there is a service and there is a line or a queue which a person joining this system has to join. If you take a typical example of a doctor, people arrive, spend some time, get served and people leave. What characterizes this queuing system or what makes it little different from the earlier models that we have seen is the fact that these arrivals and service are assumed to follow some distributions. They are not deterministic, but they are assumed to follow certain distributions. So, people arrive according to the given distribution or according to a certain distribution. The service is also provided according to certain given distributions. Now, queuing models can be of several types. First category is called a single server queuing model, where there is only one server. We also have multiple server queuing models, where there are multiple servers. A good example of a multiple server queuing model is a railway reservation system, where we could have several counters, where people who come join this line and whichever server is free, the first person will go. If this person is free next, then this person goes here and so on. So, we have a multiple server model where there are more than one server. Here there is a common line, and as soon as a server is free, this person will join, get the service and leave. Within these single server and multiple server, there are two categories. One is called a finite queue length and infinite queue length. The infinite queue length model assumes that every person who comes joins the line. For example, if already 3 people are waiting for the doctor, the 4th person will join the line and so on. There is no restriction on the number of people who are actually waiting, or there is no restriction on the length of the queue. So, the queue length can theoretically be infinite. So, it can go on and on and on. In finite queue length models, we try to restrict the queue length to a certain limit, after which we say that if this threshold limit is reached, people who come into the system do not join the system. A good example of a finite queue length model is a garage. Let us say there is a garage with a single server or a single mechanic. So, there is a mechanic here, and let us say this garage has space to park say 10 cars. Now, if for example someone is coming into the garage to give his or her car for service, if some slots are available, which means the number in the system is less than 10. Remember, these are the spaces for the garage, this is not the garage, this is the server. So, these are the places in the garage. So, if the number of cars in the garage including the one that is being serviced is 10, is less than 10, then the people, the person who is coming in will have a space to park the car, the person will leave the car and go. If when some person is coming, the garage is full, which means all the 10 slots have been taken up, including the car that is being served, then this person does not find a place to park his or her car, and the person will leave the system without joining the line, without getting served. So, such models are finite queue length models, whereas ordinarily we have infinite queue length models. Now, there is one more further classification which is called finite population models and infinite population models. If we take the example of the doctor or the reservation system or the car mechanic, they all come under the category of what are called infinite population models. This is an example of a single server, infinite queue length and infinite population. This is an example of a single server, finite queue length and infinite population models. Now, how do we categorize something as an infinite population and finite population? In this case, the population simply represents anybody who can come for treatment or service to this doctor, and therefore, it can be infinite. A good example of a finite population model is like this. If we have a factory and if this factory has about 30 machines, and if there is a dedicated maintenance team, and this maintenance team attends to calls every time these machines break down, then we have a system where the breakdown represents the arrival of a job for the maintenance team. The service is the time or the service provided by the maintenance team to attend to these breakdowns. And there is a finite population because only any one of these 30 machines, when they break down, this team will come and attend to them. So, this is an example of a finite population situation. Ordinarily, we discuss more of infinite population situations compared to finite population situations. The queuing system is also characterized by the distribution of this arrival and distribution of this service. The arrivals and services can follow any given distribution, or we can go observe the given observe physically what is happening in the queuing system, and then from the data that we can collect from what is actually happening, we can fit a corresponding distribution. But most of the times it is also observed that arrivals follow a Poisson distribution, and with arrival rate called lambda per hour. Lambda is usually denotes the arrival rate in a queuing system. It is also observed from practice that service times are exponentially distributed. So, service times are exponential at the rate of mu per hour. So, service happens at the rate of mu per hour. We also observe that Poisson distribution and exponential distribution are related, and Poisson distribution has an important property called the memoryless property, based on which we will derive some expressions for the performance of the queuing systems. So, essentially we will assume right through this lecture series that arrivals follow a Poisson distribution with lambda per hour, and service times are exponential denoted by mu per hour. Now, what is the relationship between this lambda and mu? We also need to realize that lambda by mu is less than 1, particularly if we have an infinite queue length models. If, for example, lambda by mu, if we assume lambda equal to 5 per hour and mu is equal to 6 per hour, then lambda by mu is less than 1. Now, what happens? Here lambda equal to 5 per hour means on an average 5 people enter the system every hour, which means on an average every 12 minutes a person enters the system, and on an average every 10 minutes a person gets served and leaves the system. Now, what happens when lambda by mu is greater than 1? For example, if mu were not 6 per hour and mu were 4 per hour, then every hour 5 people on an average enter the system and 4 people on an average leave the system. So, the queue length will automatically increase by 1 every hour, and this means that somebody who joins the queue will never get served. So, for a queuing system to be efficient, particularly when we have infinite queue length, lambda by mu has to be less than 1. If we have finite queue lengths, we may have lambda by mu greater than 1, because in finite queue length models, depending on what we have here, people may not join the line or join the system. Therefore, we are not that worried about lambda by mu being greater than 1. So, since some people do not join the system and go away, everybody who joins the system there will get an opportunity to be served. So, we have to be very careful, and we should have lambda by mu less than 1, particularly when we have infinite queue length models, and lambda by mu can be greater than 1. Now, if lambda equal to 5, mu equal to 6, lambda by mu is less than 1. So, this means every hour on an average 5 people enter the system, while 6 people will leave the system. So, we may be tempted to ask a question, why should we have a queue at all or a line at all when 5 people enter the system and 6 people can leave? The answer comes from the fact that this is an average or expected value of a distribution, and this 5 per hour does not mean that exactly every 12 minutes a person gets in. The inter-arrival times are exponential, the arrival rate is Poisson with lambda per hour. It means on an average 5 people enter the system following a Poisson distribution. It may happen that between 2 consecutive arrivals it could be 5 minutes, it could be 20 minutes, but at steady state if we measure, then we will have 5 people per hour entering the system. So, therefore, there will be a line, even though lambda is less than mu, there will be a line, and we are interested in analyzing the performance of this queuing system or this line. There are a couple of other things that we need to look at before we start deriving some expressions for the queuing models. There are three other terms which are often associated with queuing, and these three are called balking, reneging, and jockeying. Now, what are these? What is balking? Now, let us assume that we are going to say to book a ticket in a railway reservation system, and let us say that we have these three servers, but let us assume we are in a slight hurry, and we enter the system and we observe that there are already some 60 people waiting in the line. So, as this person enters, the person forms an opinion of how much time it is going to take for this person to finish this service and leave. And if this person thinks it is going to take a lot of time, then the person leaves the system without joining the line. So, if an arrival does not join the system and leave, then the arrival is said to balk. So, the person balks when the person does not join the line and leave. Balking can again be of two types, a forced balking and an unforced balking. Now, the example where when you enter as the 61st person in a line and you think it is going to take a lot of time, therefore, you do not join the line, there nobody is forcing you to leave. So, that is an example of an unforced balking. But on the other hand, if we go to take the mechanic example with space only for 10 cars, including the car being served, and you drive your car for service and you realize that all these 10 cars are full, then you do not have a choice, you leave the system, then such a balking is called forced balking. So, whenever we have finite queue length models, then there is a chance that balking occurs. The second phenomenon that happens is called reneging. Again, come back to this example. Let us say you enter the system to book a ticket and there are 60 people already waiting, and then you realize you wish to join and say you join as the 61st person in the line. When you join as a 61st person, you expect the line to move in a certain speed, and after a while, let us say you observe that it is actually moving slower than what you thought, and your time is running up, and then halfway through, from somewhere in the middle of the line, you decide to quit. So, you just come out of the line and you go away. Now, such a phenomenon is called reneging. So, the person joins the system, but after some time decides not to continue and simply moves out of the system, and that is called reneging. The third one is also an interesting phenomenon, it is called jockeying. For example, if this system we have multiple servers, but there is a common line. There is a common line here in this system. Now, people are waiting here. Now, depending on which server is free, the person will automatically go to the corresponding server and so on. Instead, if we had a system where there are 3 servers and each server has a dedicated line. Now, let us say you come into this system and you find about 20 people here, about 19 people here, and about 20 people here. So, there are 59 people here, let us say including the people who are being served. So, we normally would join here or we would join here, we would join one of these lines. Many times there will be a tendency to join the shortest line and so on. And then let us say you joined the shortest line as the 20th person. Now, all the 3 lines are moving towards the server and more people have actually come in and joined. But after 5 minutes you realize, let us say that you have joined, and after 5 minutes you feel that this is moving slightly faster. Say you have now become the 18th person here, but if you realize that if you actually shift this line, you can become the 17th person in this line because this line is moving faster. So, there will be a tendency to shift from one line to another line for a while and come back and so on, depending on what we think is the rate at which these lines, people in these lines are moving. Now, such a phenomenon is called jockeying. Ordinarily, jockeying happens within the first few minutes of joining the line. Once we realize that there are 4 or 5 people behind us, and if you skip this and if you are the 18th person here, and then if you jockey and you will become the 23rd person here, then you will not like to jockey. Nevertheless, jockeying happens at the beginning, and in fact, it is largely because of jockeying when we enter, we find the queue lengths to be more or less the same as we enter any queuing system which has multiple servers and dedicated lines. So, jockeying is something that is common to multiple server queuing system. Yet another parameter that we need to discuss before we derive models is called the queue discipline or the service principle. If we take the example of a doctor that we have seen, if let us say there are 6 people already in the line and you join as the 7th person, ordinarily you would know and you would expect the queue discipline to be what is called first in, first out, also called first come, first served, which is either FIFO or FCFS, first in, first out. Ordinarily, when human beings are involved and the service provider is also a human being, it is customary to assume a first in, first out service discipline or first in, first out rule to send the next person into the system. When we do not have human beings in the system, the service discipline can vary or can change. There are times we can have a last in, first out system and so on. But most queuing models are also derived under the principle that first in, first out system operates. Steady state models usually are independent of the service discipline, whereas transient models involve the discipline and are derived using first in, first out models. So, with this kind of an introduction, we will look at 4 different queuing models in this lecture series. We will not consider aspects like balking, reneging and jockeying. We are not going to consider finite population. We will consider single server models, multiple server models, and within each of these we will consider finite queue length and infinite queue length. So, 2 types of servers, single server and multiple server models, and 2 types of queue lengths, which is finite queue length and infinite queue length, would give us 4 basic models of queuing theory. And we will first look at a single server infinite queue length model, which will be the first, then single server finite queue length model, multiple server infinite queue length model, and multiple server finite queue length models will be the order in which we will study these models. So, we start our discussion on the single server infinite queue length model, and we will represent this model following a certain notation. So, the notation that we will use will be called M1 infinity infinity model. This is part of a very familiar notation called the Kendall's notation. We have used a portion of the Kendall's notation. I have left out one of the spaces in the Kendall's notation. Now, this M characterizes the arrival, this M characterizes the service. The M and M indicates the memoryless property of the arrival and the service, or Markovian property of the arrival and the service, and these come here because of the assumption that it is Poisson that follows the Markovian property of lambda per hour. This is exponential with mu per hour. Now this 1 represents the number of servers. So it is a single server model. This infinity is the queue length. So it is an infinite queue length model, and this represents the population. So it is an infinite population model. So MM1 infinity model would mean a single server model with Poisson arrival and exponential service following the memoryless property. The infinity represent infinite queue length and infinite population model. So the queuing system will be like this. There is a server who serves at the rate of mu per hour. There are arrivals at the rate of lambda per hour. Now, in the memoryless property, we are going to assume that the behavior of the system does not have any memory, and therefore it does not take into account the earlier states of the system in order to define the present states of this system. So the memoryless property also helps us in one important property, which is an important assumption here, that during a very small interval only one event will take place. One event takes place in a small interval h. An event is either an arrival or a service. It is either an arrival or a service. Now, what we want to study is, in a system like this, at steady state, what is the probability that at steady state this system has 0 people, 1 person, 2 people, and so on. This can go up to infinity. What are all the other things we wish to study in this system? Now, typically from a user point of view or from a customer point of view, the customer is ordinarily interested in 4 important parameters. Now, these 4 parameters are called length of the system, length of the queue, waiting time in the system, and waiting time in the queue. Now, what is this length of the system and length of the queue? Length of the system is the expected number of people who are actually in the system, including the person who is being served. Length of the queue is the expected number of people who are waiting for service in this system. So, obviously, there is a relationship between these two. A person who enters the system would actually like to know when the person will actually leave the system. So, the person is interested in waiting time in the system, and there are times the person is interested in waiting time in the queue. Normally, if we are interested in going for specialized services, say a doctor or a legal service, then the time taken by the server also matters. And then there are times we are worried about waiting time in the queue, so that we are worried about when our service is exactly going to start. In such a situation, we are concerned about waiting time in the queue. Now, if we have a restriction on the total time that we want to spend in the system, then we look at waiting time in the system. Ordinarily, these are represented as Ls, Lq, Ws, Wq. It is also obvious that these two are related, and there is a relationship between Ls and Ws, which means all four of these are actually related to each other. So, if we derive an expression for one of them from first principles, we can actually use the relationship among these parameters to derive expressions for the rest of them. So, this queuing system finally is going to be measured for equations that define Ls, Lq, Ws and Wq. Now, these are expected values, expected number of people, expected waiting time and so on, and therefore, these depend on the probability that there are n people in the system. So, probability that there are 0 people in the system is P naught, P1, P2 and so on. This can go up to infinity. So, we are interested in getting expressions for P naught, P1, P2 etc., which represent the steady state probabilities that there are 0, 1, 2 etc. people in the system. Based on these probabilities, we will derive expressions for Ls, Lq, Ws and Wq. Now, in order to get expressions for these P naught, P1, P2 etc., the two important things or the three important things that we know are lambda, mu and the number of servers. In this case is 1, it is called C equal to 1. C represents the number of servers. So, the input values to the queuing system are lambda, mu and C. The output values are Ls, Lq, Ws, Wq. The intermediate values are P naught, P1, P2 etc. So, we start deriving some expressions to get a general Pn, that probability that there are n people in the system in terms of lambda, mu and C. Once we get an expression for Pn, we can substitute for various values of n as 0, 1, 2 and so on, and then we can get these, from which we can go back and get these expressions. So, let us start deriving some expressions for this. Now, Pn of t plus h means the probability that there are n people in the system at time t plus h, where h is small. Now, there will be n people in the system at time t plus h if we had n minus 1 people at time t, and during this small period h, one person has arrived and no person has left. So, Pn of t plus h, probability that we have n people at time t plus h, can happen when there are n minus 1 people at time t, and in the small period there is one arrival and no service. This can also happen if there are n plus 1 people, there were n plus 1 people at time t into there was one service and no arrival, plus there were n people into no arrival and no service. Now, this is obvious that we have n people here. Now, that can happen if we had n plus 1 at time, this is time t, this is time t plus h. So, one way it can happen is there were n plus 1 people here and one person has left. So, 1 service 0 arrival, or we could have had n minus 1 people here and in the small gap we would have 1 arrival 0 service. We could have n people here, we could have had 0 arrival 0 service or 1 arrival 1 service. We are not considering other possibilities for the reason that in a small period only one event can take place and the event is either an arrival or a service. Therefore, we are not looking at n plus 2 people in the system and 2 people living in the small period h. Similarly, we are not looking at any other value other than n minus 1. We do not say n minus 2 people were there and there were 2 arrivals. So, now coming back to this n, two things can happen. There is a 0 arrival and a 0 service, there is a 1 arrival and 1 service. Now, 1 arrival and 1 service means 2 events, and we have made an assumption that we will not have more than 1 event taking place. So, we do not consider this as part of defining the probability that there are n people in time t plus h using n in time t. That is the reason I have not written the fourth step, which is 1 arrival and 1 service. That it means there are 2 events and therefore, we do not write that. Now, these things come from the memoryless property of this system, which also says that it is not state dependent as such, and the system does not respond to what it was doing in earlier periods. So, system does not have memory and therefore, does not carry whatever it was doing in earlier stages than what we are looking at. Therefore, based on the memoryless property which the Poisson and exponential distributions provide us with, we can write this expression. Now, coming back to this expression, now probability of one arrival during any given period is lambda h, and probability of one service is given by mu h. So, when we do this, we can write this as P n of t plus h is equal to P n minus 1 at time t into probability of one arrival, which is lambda h, and probability of no service is 1 minus mu h, because mu h is the probability of one service or one person leaving the system. So, the probability of 0 person leaving the system is 1 minus mu h. We do not consider 2 persons leaving, 3 persons leaving and so on. Therefore, probability that 0 person leaves plus probability that 1 person leaves is equal to 1. Therefore, probability of no service will become 1 minus mu h plus P n plus 1 t into one service and no arrival. So, one service is mu h, no arrival is 1 minus lambda h. For the same reason, one arrival is lambda h, therefore, 0 arrival is 1 minus lambda h plus P n of t into no arrival and no service. So, 1 minus lambda h into 1 minus mu h. Now, this is the expression that comes from this. This we can simplify. We not only we simplify and we leave out the higher order terms. So, on simplification, this will become P n minus 1 of t lambda h minus lambda mu h square. So, lambda mu h square is a second order term. So, we leave out the second order term. So, we get P n minus 1 t into lambda h plus P n plus 1 at time t into mu h plus P n of t into 1 minus lambda h minus mu h plus lambda mu h square. So, second order term is left out. So, this into 1 minus lambda h minus mu h. Now, we bring this P n of t to the left hand side, we will get P n of t plus h, P n probability that n people are there and dividing the whole thing by h, h is common in all of them, dividing the whole thing by h would give us P n minus 1 at time t into lambda plus P n plus 1 at time t into mu minus P n at time t into lambda plus mu, because this 1 will come to the other side divided by h. Now, from this equation, if we apply the steady state condition, which means the change of P n by t to the interval h will be 0 at steady state. At steady state, the probability is not going to be time dependent. So, when we apply the steady state condition, this portion becomes 0. So, we have P n minus 1 into lambda or lambda P n minus 1 plus mu P n plus 1 is equal to lambda plus mu P n. So, if P n plus 1 represents the steady state probability that there are n plus 1 people in the system, P n minus 1 represents the steady state probability that there are n minus 1 people in the system, and P n represents the steady state probability that there are n people in the system, then the equation that is joining them is lambda P n minus 1 plus mu P n plus 1 is equal to lambda plus mu into P n. So, we call this as equation number 1. Now, we go back and do this, make a slight difference here, and then we derive one more expression here, which is this. Now, probability that there is one person in the system at time t plus h will be probability that there are now probability that there are 0 people in the system at time t plus h will be probability that there is one person in the system at probability that there are 0 people in the system at time t plus h is probability that there is one person in the system at time t and there is one service and no arrival, plus probability that there are 0 people in this system and there is no arrival and no service. Now, this when we expand, we will get P naught time t plus h is equal to P 1 of t into no arrival and one service, which is 1 minus lambda h into mu h. Probability of one service is mu h, probability of one arrival is lambda h. So, probability of no arrival is 1 minus lambda h plus P 0 t into probability of no arrival is 1 minus lambda h, but probability of no service is 1 because there are already 0 people in the system. So, there is no service. So, probability of no service is 1. So, please note this difference. Earlier when we had other than 0, then there could be a service. So, probability of service was mu h, probability of no service was 1 minus mu h. Because we have 0 people in the system, probability of no service is 1. Now, when we expand this, P naught of t plus h is equal to P1 of t, expanding and leaving out the higher order terms, into mu h plus P naught of t into 1 minus lambda h. Now, taking this to the other side, P naught of t plus h minus P naught of t by h will become P1 of t into mu minus P naught of t into lambda. Now, again applying the steady state conditions. So, at steady state the rate of change of P naught with respect to h is 0, because we assume that P naught is a steady state probability. So, there is no change with respect to h. So, this will become 0 and P1 of t will simply become P1 and P naught of t will simply become P naught. So, this will give us a second equation, mu into P1 is equal to lambda into P naught as the second equation. Now, this is the second equation that we have. Now, from these two equations, so the first thing that we can derive is P1 is equal to lambda by mu into P naught. So, this is the first thing that we can derive. Now, we go back and apply this to this one. So, we get lambda into P1 so put n equal to 1, we get lambda into P naught plus mu into P2 is equal to lambda plus mu into P1. So, this is lambda P naught plus mu P2 is equal to lambda P1 plus mu P1 when we expand. Now, from this we know mu P1 is equal to lambda P naught. So, this is lambda P1 plus lambda P naught. So, the lambda P naught gets cancelled. From this we get P2 is equal to lambda by mu into P1, and we already know that P1 is equal to lambda by mu into P naught. So, this is lambda by mu the whole square into P naught. We normally describe this lambda by mu as rho equal to lambda by mu. So, we have P1 is equal to rho P naught, P2 is equal to rho P1 equal to rho square P naught, and in a similar manner we can derive P3 is equal to rho P2 which is equal to rho cubed P naught, and any general Pn is equal to rho power n P naught. Now, this we can derive by progressively substituting in the earlier equation. So, these are the important equations that relate this. Now, at the moment we know now that P1 is equal to rho P naught, P2 is equal to rho square P naught, and so on. We still do not know the actual values of P1, P2, P3 or a Pn, because they have all been derived as dependent on P naught. So, unless we know P0, we cannot find out the values of P1, P2, P3 or a general Pn. So, to find out P0, we go back to the normal rule that the sum of the steady state probabilities is equal to 1. So, we have P naught plus P1 plus P2 plus up to infinity is equal to 1. So, this would give us P naught plus rho P naught plus rho square P naught etc. up to infinity is equal to 1. So, this is P naught into 1 plus rho square plus up to infinity is equal to 1. Now, an interesting thing is this is an infinite series, which is the first one. It is a geometric series because you have 1 rho square etc. So, we know the sum to infinity terms of a geometric series as a by 1 minus r, provided r is less than 1. We also know that rho being lambda by mu should be less than 1 for an infinite population model. So, when lambda by mu or rho is less than 1, we can apply the infinite geometric series summation formula to get P naught into, this will have a by 1 minus r. So, 1 by 1 minus rho is equal to 1, from which P naught is equal to 1 minus rho. So, P naught equal to 1 minus rho is an important equation for a MM1 queuing model or MM1 queuing system. Once we know that P naught is equal to 1 minus rho, now P1 is equal to rho P naught, which is rho into 1 minus rho, and a general Pn is rho power n P naught, which is rho power n into 1 minus rho. We know rho as lambda by mu, therefore, we can calculate P naught, P1, P2, any Pn. So, we started off by saying that the inputs are lambda, mu and c, and in this case, because it is a single server model, it is lambda, mu and 1, or essentially only rho, which represents lambda by mu. It is not even necessary to have the individual values of lambda by mu or lambda and mu. If we know rho, which is the ratio of the arrival rate to service rate, which is less than 1, then we can find out the expression for P naught, P1 up to any Pn. But it does not end there, because we said earlier that we are interested also not only in P naught, P1, P2 up to Pn, we are also interested in the expressions for Ws, Wq, Ls and Lq. So, we need to derive expressions for Ls, Lq, Ws, Wq in terms of P naught, P1 etc., which means in terms of rho. So, we will do that next. Now, Ls is the expected number of people in the system, and Ls is given by sigma j equal to 0 to infinity j pj. Ls is like an expected value. So, it is j, the number of people, multiplied by the steady state probability that so many people are there in the system. So, this is like saying 0 into P naught plus 1 into P1 plus 2 into P2 etc. n into Pn. So, this will give us sigma j, Pj is rho power n P naught or rho power j P naught. Now, we take one P naught outside and a rho outside. So, this is P naught into rho into sigma j rho to the power j minus 1. Now, this is P naught rho into sigma d by d rho of rho power j, and then we follow the usual idea that when we have this summation and a differentiation, we can switch this without losing anything in the expression. So, we get P naught into rho into d by d rho of sigma rho power j. Now, this will give us P naught into rho into d by d rho of sigma rho power j. This is 1 plus rho square etc. up to infinity. So, this is again an infinite geometric series with rho which is lambda by mu, rho less than 1. So, this will be P naught rho into d by d rho of 1 by 1 minus rho. So, this will be P naught rho into 1 by 1 minus rho will give minus 1 by 1 minus rho the whole square into another minus 1. So, we get 1 by 1 minus rho the whole square. This again P naught is 1 minus rho. So, this is 1 minus rho into rho by 1 minus rho the whole square. This is rho by 1 minus rho. So, we get an expression for Ls as Ls is equal to rho by 1 minus rho. So, expected number of people in the system is rho by 1 minus rho. Now, we need to write down the expressions for the other ones. Now, expected number of people in the queue is equal to the expected number of people in the system is equal to expected number of people in the queue plus expected number of people who are being served plus expected number of people who are being served. So, we can get Ls is equal to Lq plus lambda by mu. Lambda by mu or rho represents the expected number of people who are being served. So, from this we can get the expression for Lq we can get once we know Ls. Now, Ls and Lq are related as Ls is equal to lambda Ws and Lq is equal to lambda Wq. Now, this is the relationship between Ls and Lq and Ws and Wq. These two are the well known Little's equation which capture the relationship between the length of any system and the time associated with this system. So, with this we can find out Ls, Lq, Ws and Wq. We will work out a numerical example and continue our discussion in the next lecture.